Okay, thanks a lot. Hello, everybody. Happy New Year. Tonight's subject is all about magnetos. Whoop, didn't mean to do that. And we have a lot of stuff to discuss. We're going to be talking about the construction of magnetos, the various components, how they work together, talk a little bit about common failure modes of magnetos. I'll show you some ugly pictures. We're going to talk about mag timing, and there's actually two different kinds of mag timing, internal timing and external timing. We'll talk about how magnetos are set up to start the engine. Starting is a particular problem with the Magneto Ignition engines, and there are two different approaches to getting a Magneto Ignition engine to start. So we'll talk about that a little bit. We'll talk about the mag check, both the pre-flight mag check and in-flight mag checks, which I'm a strong proponent of. Talk a little about some unique problems that we have with magnetos for airplanes that operate up at high altitudes, like up at the flight levels. Talk about the importance of 500-hour inspections on magnetos, and talk a little bit about the different makes and models of magnetos and comparing the pros and cons of each. And finally, just a quick word about some troubleshooting procedures. So let's proceed. We're going to talk about the various key components of a magneto. This is an exploded diagram of a slick mag. There are two main brands of magneto: Slick, which is now manufactured by Champion, and Bendix mags, which are manufactured by Continental. As you can see, there's a lot of pieces and parts, and let's talk about them a little bit, about what they do and how they work together. The heart of the magneto is the rotor. It's also sometimes referred to as the rotating magnet assembly, because it's a very, very strong permanent magnet mounted on a shaft. Runs in some bearings in the magneto case, and the fact that that it's a permanent magnet is why they call the device magneto. It is rotated by a drive gear in the engine. The rotor turns at crankshaft speed for 4-cylinder engines, and at 1.5 times crankshaft speed for 6-cylinder engines. The rotor rotates inside of a coil assembly, and because it's a strong permanent magnet, as it rotates inside the coil assembly, it induces an AC current in that coil assembly. It actually generates 2 pulses per rotor revolution, 1 in each direction, as the North Pole goes past the pole pieces, and then the South Pole goes past the pole pieces. The amount of energy that it generates in the coil, of course, is a function of how fast the rotor is turning, and also is a function of magnet strength. Now, these magnets retain their magnetism very, very well over time. When the mags are ultimately overhauled, one of the things that is done is that the rotor is remagnetized. The rotor rotates inside of a coil assembly, and this is what it looks like. The coil assembly is potted in a very strong epoxy case, and it has 3 connections to it. It has a ground wire, that's the white wire on the left. It has a wire connected to the hot side of the primary coil, that's the green wire on the right, and it actually connects to the breaker points. And it has a high voltage tab, which is connected to the hot side of the secondary. That tab it actually is connected to the magneto's distributor by means of a carbon brush, which you'll see in a subsequent slide. But you can see on that high voltage tab, you can see the impression of the little carbon circle where the brush was riding on that high voltage tab. So that's what the coil looks like, and again, it has 3 connections: a ground, a wire to the hot side of the primary, and a tab connected to the hot side of the secondary. The primary winding of the coil is typically about 200 turns of heavy gauge copper wire wound on a laminated iron armature. One end of it is permanently grounded to that white wire, which you can actually see is grounded right to the magneto case. And the other end connects that green wire, which goes to the breaker points. The secondary winding, which is also inside the coil assembly, has about 20,000 turns of very, very fine copper wire. About, I think I did that wrong. It says 200 times step up. It really should read 100 times step up. But at any rate, any voltage that's induced in the primary is stepped up 100-fold in the secondary. And so the secondary puts out very high voltage. Again, one end of the secondary winding is permanently grounded via that white wire that is grounded to the magneto case, and the other end is connected to the high voltage tab that the carbon brush rides on. This is the cam and breaker point assembly. The cam is on one end of the rotor shaft. This particular picture is of a slick mag, and you can see that the cam on a slick mag is simply a piece of plastic that is inserted in a slot in the rotor shaft, and so it has 2 lobes, plastic lobes that are sticking out, one on either side, and again the points will wind up opening twice per rotor revolution. In the TCM or the Continental Bendix mags, the cam is a real honest-to-God metal cam with 2 lobes on it. It's made of metal rather than plastic. The plastic is used in the slick mags. And you can also see the breaker point assembly. There are 2 tungsten contacts, one that is permanently grounded and the other one that's connected to that green wire to the coil primary. So when the points are closed, the primary, the green wire is connected to ground, and when the points are open, the green wire is open and not connected to anything. And the cam opens the points once every half revolution of the rotor, or twice per revolution. The points are normally closed, and when the points are closed, the primary, the 2 ends of the primary are connected to one another. They're both connected to ground. So when the magnet in the rotor rotates, it induces a current in that primary that flows continuously round and round through the coil primary winding, which creates a powerful magnetic field in the coil's laminated iron armature. At the moment of ignition, the cam opens the points and breaks the loop, which causes the magnetic field in the coil to collapse suddenly. And the collapse of that field creates a voltage spike in the primary of 200 to 300 volts, and it induces a very high voltage spike in the secondary, typically 20 to 30,000 volts. There is a condenser, sometimes called a condenser, sometimes called a capacitor, 2 different words for the same thing, and it's connected across the breaker points. The purpose of the condenser is to prevent arcing between the points as they open. As the points open, there's this very high voltage, or relatively high voltage pulse, 200 or 300 volts, that's induced in the primary. And if it wasn't for the condenser, that would cause arcing across the points as they start to open, as the cam starts to open the points, and would cause the points to pit and erode, and they wouldn't last very long. So the condenser absorbs the that energy, and as the points just start to open and prevent the arcing across the points. Also, the condenser provides a predictable collapse of the magnetic field that isn't super sensitive to the condition of the points. So if the points are start to erode a little bit, the collapse of the field as the points open remain pretty constant, and so the characteristics of the mag remain constant even as the points start to wear a little bit. But if the condenser goes bad, as it does from time to time, and these things they deteriorate with age, and after 6 or 7 years they can start going bad. And if the condenser goes bad, then the points will arc, and they'll start to pit quite badly, and that's one of the causes of magneto failure. Here's a kind of ugly little schematic diagram that shows how this stuff goes together. You've got the primary that is connected to the points. There's a capacitor across the point contacts or condenser to prevent arcing at those points. The secondary, this shows it connected directly to the hot terminal, the spark plug. In fact, it actually goes through a distributor which connects it to the appropriate spark plug, the appropriate one of the 4 or 6 spark plugs on the engine. But this diagram, for simplicity, leaves out the distributor. Here is the distributor. It's a plastic gear. It's plastic because plastic doesn't conduct electricity, and there's real high voltage here. The gear rotates in a bearing, an oilite bearing, a permanently lubricated bearing, and it has a copper finger that rotates around and comes in close proximity with one of 4 or 6 contacts in the distributor block. The finger doesn't actually touch the contacts; it just comes very close to them, and this is what's called a jump gap distributor. So there isn't actually metal-to-metal contact, but the finger comes close enough to the contacts that the high voltage pulse from the coil jumps across that gap and goes to the appropriate spark plug. The distributor is geared down so that it rotates at half crankshaft speed. So compared to the rotor, it's geared down by a factor of 2 if it's a 4-cylinder mag, or by a factor of 3 if it's a 6-cylinder mag. But the distributor always rotates at half crankshaft speed because it takes 2 crankshaft rotations to put each of the cylinders through through their 4 cycles. As I said, the rotating wiper attached to the distributor gear passes in very close proximity to the distributor block electrodes, close enough that the spark can jump that gap and proceed via the appropriate ignition lead to the spark plug and fire the spark plug. It's extremely important that the inside of the distributor block be scrupulously clean, because any contamination inside the mag can result in a conductive path that can cause internal arc over inside the mag. Internal arc over will cause ignition anomalies. It'll make the engine run real rough, but secondly can actually cause things to heat up inside the mag to the point where things start to melt and then really bad things happen. One of the main failure modes that we see in magnetos, and we've actually seen a really quite alarming number of them in recent years, are distributor gear failures. Here are some examples where the plastic distributor gear winds up losing a tooth or a series of teeth. And of course, once it does that, the distributor just starts going berserk and firing spark plugs in the wrong at the wrong timing, and can cause the engine to go nuts. Now, one of the reasons that we have 2 magnetos on every engine is so that if a failure like this happens, we can turn off the magneto that's causing the problem and run the engine on the magneto that's still healthy. But one of the things that I have noticed with some alarm is that in the last few years, we've in just the fleet of aircraft that my company manages, several hundred aircraft, we've had something around a half a dozen catastrophic magneto failures of this sort. Some have occurred up at high altitude, some have occurred down in the pattern, some have occurred IFR, some VFR. A number of them have occurred with extremely experienced pilots or flight instructors flying the airplane. And in not one single case did the pilot, when the engine started running extremely rough or threatening to quit, in not one case did the pilot have the presence of mind to try turning off one mag or then the other in order to turn off the mag that's going berserk and run on the single mag that's still running properly. And so, you know, having 2 mags is nice, but doesn't help a lot unless the pilot turns off the bad mag when it starts doing funny things. And it seems like pilots have this notion that the only kind of mag failure is one where the mag just stops working and stops firing. But that's not true. The most common cause of mag failure that we've been seeing are distributor gear problems like this, where the mag keeps firing, it just fires the wrong plugs at the wrong time and causes the engine to do really horrible things. And the resolution to that is to figure out which mag is bad and turn it off. But for some reason, most pilots just don't seem to have the presence of mind or the presence of checklist or whatever to do that. So that's the reason I'm making a point of this. Another failure mode that we have seen specifically with slick mags, and it got so bad actually that an AD came out, was failures in which the carbon brush started failing and spreading carbon dust, conductive carbon dust on the inside of the mag. The mag would then arc over through these paths of carbon dust and start melting things. And you can see that this is the main distributor gear support, which has been totally wrecked by arc over inside the mag due to the carbon brush deteriorating. In this particular case, it turned out that that Slick had a bunch of bad brushes get into the system, and they would start deteriorating at an accelerated rate and cause just wreak havoc inside the magnetos. The magneto is connected to the ignition switch in the cockpit. If it's a single, it's typically a key-operated rotary switch like this. If it's a twin, it's typically a series of individual toggle switches. And there are a number of different sorts of switches, but the cockpit switch that turns the mags on and off connects to the mag via a wire called a P-lead. To turn off the mag switch shorts that P-lead to ground, so that even when the points open, the top of the primary is grounded through the P-lead, and so the magnetic field never gets to collapse and never gets to fire the plugs. The P-lead is shielded wire with the shield grounded to the magneto case. It's very, very important that the P-lead be shielded and that the shield be properly grounded, because if it's not, then the P-lead winds up becoming a big antenna that radiates all sorts of impulse noise and raises havoc with your radios. Very common problem is to start hearing impulse noise, static in the radios, and the most common cause of that is that the P-lead ground has become broken or disconnected, or the screw to which it's grounded has come loose or something like that. And if the P-lead is not grounded, it will radiate all sorts of ignition noise into the radios. It'll also pretty much shut down a GPS, and it will cause an ADF to go berserk. If the P-lead itself breaks or gets disconnected or is accidentally left off, we have a condition called a hot mag, where the magneto cannot be shut off from the cockpit. And that can be a potentially dangerous situation because in many aircraft, if there's a hot mag and you manually rotate the prop, the engine might fire even though you think everything's turned off. And as I said, if the shield becomes ungrounded, you'll get a lot of ignition noise in your radios. Magneto timing is important. It's very, very critical that the spark occur at the correct time. There's actually two different kinds of timing of magnetos. One called internal timing, otherwise known as EGAP, and the other called external timing, otherwise known as timing the magneto to the engine. The EGAP, or internal timing, is adjusted normally when the magneto undergoes its 500-hour inspection, which we'll talk about. And it's an adjustment that's made internally to the magneto. And its purpose is to make sure that the points open at the point of maximum induced voltage in the primary in order to generate the hottest possible spark. Over time, as the points wear and as the cam wears, particularly the cam wears in a slick mag, or the cam follower wears in a Bendix mag, the EGAP, or the internal timing, will drift off, and as it drifts off, the mag's output voltage will gradually get lower and lower. So if the EGAP is allowed to drift off far enough, the mag's voltage will be impaired enough that it can be hard to start the engine, and the ignition performance will be less than optimum. Again, to adjust the internal timing, the mag has to be opened up, and normally we do this at a 500-hour inspection. The external timing is adjusted by rotating the magneto on its mount to the engine, and external timing adjusts exactly when the spark plug fires. Normally, the engine specifications and the engine data plate will indicate what the proper timing for the mag is. Typically, it's something between 20 and 24 degrees before top dead center. There are some engines that are actually timed at 28 degrees. It's very, very important that the mags be adjusted so that the spark fires exactly at the right time. Normally, this is adjusted. This is checked and adjusted at every annual or 100-hour inspection. And as I said, this does not require disassembling the magneto or removing it from the engine. You check it with a timing light, which I'll show you in a minute, and then if it needs to be adjusted, you just loosen the mounting nuts that secure the mag to the engine and rotate the mag slightly one way or the other to get the timing correct. This is the typical equipment that's used for adjusting the external timing of the mag, or timing the mag to the engine. There's a timing indicator with a degree scale, and there's a mag timing light that connects to the magneto P leads and lets you determine exactly when the points are opening. And you need to set it so that the points open at exactly the number of degrees before top dead center that's indicated in the engine specifications and on the engine data plate. Nowadays, this timing indicator that's illustrated here is sort of the old-fashioned kind. And typically it's hard to get much closer than about a degree of accuracy. Nowadays we tend to use digital inclinometers, digital levels that you can buy down at Home Depot, and they're accurate to 1/10 of a degree, and it's a better way to do it. Starting the engine with a Magneto Ignition system is a special challenge. And the reason is because for really two things. First of all, at the typical cranking speed of an engine, which is about 50 RPM, in other words, how fast the starter motor will turn the engine, the magneto rotor isn't turning fast enough to generate enough energy to fire the spark plugs. A mag's what's called a coming in speed, which is the minimum RPM that is required to fire a spark plug, is typically something north of 150 RPM. And starter motors just don't crank engines that fast. So getting enough voltage out of the magneto to start the engine is a problem. The other issue is that even if the mag could generate enough voltage at 50 RPM, the timing of the spark, which is normally, as I said, 20 to 24 degrees before top dead center, if the spark plug fired at 20 to 24 degrees before top dead center with the engine cranking at 50 RPM, it would cause the engine to kick back. So in order to start the engine, we have to retard the timing by 25 to 35 degrees from its normal timing in order that the spark actually ignite something slightly after top dead center rather than 20 to 24 degrees before top dead center. So we need to have a scheme for accomplishing both of those things. First of all, generating enough voltage to fire the spark plug, and second of all, retarding the timing in order to allow the engine to start without kicking back. And there are two schemes for doing that. The most common is called an impulse coupling. Impulse coupling is a mechanical device that is attached to the magneto's rotor shaft and sits between the magneto and the engine drive gear. I'll show you a picture of one of these on the next slide. But it basically consists of a clever arrangement of springs and flyweight operated pawls that cause, as the engine tries to turn the mag, it actually locks the mag in place and causes the engine to wind up a spring. And then after the spring has been wound through 25 to 35 degrees of crankshaft rotation, the pawls release and allow the spring to snap the mag over much more rapidly than the speed of the engine, which allows it to generate enough voltage and also retards the ignition by the amount required in order to get the engine to be able to start. The other approach is called a retard breaker magneto, or otherwise known as a shower of spark system, which was a trademark that Bendix used for this. And in this scheme, instead of having the impulse coupling with the pawls and the springs and all that stuff, the magneto contains a second set of breaker points that are timed to the starting time. And so when you're starting the engine, the mag runs on this second set of retard breaker points instead of the normal breaker points, which causes the spark to fire after top dead center instead of before top dead center. And the system also contains something called a starting vibrator, which is sort of like a little doorbell buzzer, which provides pulsed DC pulses from the aircraft's battery to provide the voltage to generate the spark, since the mag is turning too slowly to generate enough voltage by itself. And so the retard breaker system again uses a second set of points and uses a starting vibrator, and between those two components it's capable of starting the engine. This is what an impulse coupling looks like. Over the right, you can see what the spring inside the impulse coupling is like, and the engine winds up that spring. Those pawls prevent the magneto from turning while the spring gets wound up, and then when the spring is wound up by about 35 degrees, the pawls suddenly release and the spring snaps the magneto through, generating a sufficiently high voltage to fire the plugs, and retarded by about 35 degrees. Once the engine starts, centrifugal force causes the flyweights to retract the pawls, and the impulse coupling stops doing its thing, and the engine just drives the magneto directly. When you shut down an engine that has impulse couplings, as the engine comes to a halt, the last few rotations, you'll hear a snap snap as the impulse coupling starts to do its thing again. So you can always tell by ear whether an engine has impulse couplings or shower of sparks, because the impulse coupling makes a snapping noise if you turn over the prop by hand. Also makes a snapping noise when the engine is shutting down, and the shower of sparks doesn't make any noise. The shower of sparks system, or retard breaker system, looks vaguely like this. It's got a second set of breaker points in the mag, timed to a starting timing, and when you have the start switch energized, it causes the mag to fire using the retard breaker rather than the normal breaker. Then when you take you release the start switch, it goes back to using the normal advanced breaker. And there's also, as I said, a vibrator that causes pulsed DC from the ship's battery to be supplied to the retard breaker to provide voltage for the starting sparks. Here's a diagram of what the shower of sparks system or retard breaker system looks like. It's a simplified diagram. It's actually fairly complicated, but the start switch in a shower of sparks system has a whole bunch of different contacts that in addition to grounding out the P lead, also winds up energizing the ignition vibrator and connecting it to the retard breaker points. Talk a little bit about mag checks. The traditional mag check that's in your POH is what we call an RPM drop-off test. The procedure is slightly different depending on whether you're operating a Continental engine or a Lycoming engine. Continentals normally specify doing the mag check at 1700 RPM, and you switch from both to one mag, then to the other mag, and typically the POH will say that the max acceptable drop-off is 150 RPM, and the max difference between the left and right mag is 50 RPM. That can vary a little bit from POH to POH, but that's generally the parameters for most Continental engines or direct drive Continental engines. Lycoming is a little bit different. And in fact, Lycoming changed their guidance a year or two ago in something called Service Instruction 1132B, which is probably more current than what's in your POH if you have a Lycoming powered airplane. Calls for checking controllable pitch prop engines at 50 to 65% power and checking fixed pitch prop engines at 1800 to 2000 RPM. I think most of the POHs I've seen for Lycomings call for a run up at 2000 RPM. The new thing that was introduced in the service instruction is that the old guidance from Lycoming used to be to do the mag check at full rich, and the new guidance is to do it lean to peak RPM, which is basically a best power mixture. And Lycoming's guidance calls for a max drop-off of 175 RPM and a max difference of 50 RPM. Now, all that manufacturer guidance was written assuming that the aircraft has Jurassic engine instrumentation. Nowadays, a lot of us, hopefully most of us, have some kind of a digital engine monitor with EGT probes on each cylinder. And if you have a digital engine monitor, then I recommend that you ignore the RPM drop-off and pay attention to the EGTs, because it's a much, much better indication of what the ignition system is doing than the old RPM drop-off. And basically, you want to just conduct the pre-flight mag check the same at the same RPM and so on as you did before. But instead of looking at the TAC, you want to be looking at your engine monitor. When you turn off one mag, all of the EGT bars should rise. None of them should fall. They should typically rise between 50 and 100 degrees Fahrenheit. It's fairly common for them not all to rise quite the same amount. In fact, it's very common for the odd-numbered cylinders to rise more than the evens, or vice versa, depending on which mag you're running on. That's absolutely normal. But you want to make sure that all the EGT bars rise, and that once they have risen, they remain pretty stable at the higher values, and that the engine runs smoothly on one magneto. And then you try the same thing again with a second magneto. And that's the way I do my mag checks. I don't pay attention to the tachometer. I watch the engine monitor. Now, the pre-flight mag check, whether you're doing it using the TAC or using an engine monitor, is not a very demanding or discriminating test of the ignition system, and in fact will only catch the grossest of problems. A much, much better test is to do an in-flight mag check. To do an in-flight mag check, you have to have an engine monitor. Obviously, you're not going to get any RPM drop-off, particularly if you have a controllable pitch prop, because the prop will keep the RPM constant. So what we're looking for in an in-flight mag check is rising EGTs, stable EGTs, engine running smoothly on one mag. The best in-flight mag check is performed at the leanest possible cruise setting, preferably lean to peak. The leaner the mixture, the more difficult it is for the spark plug to ignite it. So if you want to put the ignition system through a maximum stress test and really check out its condition, you want to perform this thing as lean as you possibly can. And as I said, if the engine is capable of running lean to peak, it's best to do this test lean to peak. We want to switch off each mag individually, leave the engine running on one mag for at least 30 seconds. Make sure that all the EGT bars rise and that none of them fall. Again, if the odds rise more than the evens or vice versa, that's normal. Ensure that the engine is running relatively smoothly on each mag individually. Now, the engine will always run a little bit rougher on one mag than two, and that's particularly true if the mixture is really lean. But if it's running rough enough that your passenger says, "What's wrong with the engine?" then that's probably too rough. If you have a constant speed prop, of course, do not expect an RPM drop-off when you do this, because the controllable pitch prop will keep RPM constant. We're looking at EGTs here. We're not looking at RPMs. Quick note about high-altitude operation. For turbocharged airplanes that fly up at the flight levels, there is a unique problem that's called high-altitude misfire. As the airplane climbs to higher and higher altitudes, the more the manifold pressure is boosted above outside ambient, the more difficult it is for the magneto to fire the spark plug. And if it gets difficult enough to fire the spark plug, the spark may arc over inside of the magneto distributor block, as opposed to arcing over at the spark plug the way we want it to. If that happens, the engine will get extremely rough. It actually is quite a scary experience. You'll find that if this happens, reducing manifold pressure makes the problem go away, and descending to a lower altitude makes the problem go away. If this happens to you after you get back on the ground, you want to have the mags pulled and opened up, because arc over inside the distributor cap can cause significant internal damage to the magneto, similar to the picture that we saw with the carbon brush problem. There's a lot of plastic parts inside magnetos, and if there's significant arc over inside the mag, it can start melting those parts. As the spark plug gaps get larger, the likelihood of this sort of high altitude misfire increases. So for airplanes that fly up at the flight levels, it's really important to do regular spark plug maintenance and to keep the spark plug gaps tight. Most spark plugs are specified to have a gap between 16 thousandths and 21 thousandths, and you want to try to keep it at the tight end of the range to provide maximum protection against high altitude misfire when you're flying up the flight levels. The two methods of preventing high altitude misfire are to use a physically large magneto, where the electrodes inside of the distributor are so far apart that it's almost impossible to have arc over. I'm speaking specifically of the Bendix S1200 mags, which we'll see on the next slide or the slide after that, which are very large magnetos. They're the ones I use in my airplane, and they're very, very capable at high altitude because the spacing between the electrodes is so large. But those mags are big enough that they won't fit on certain engine installations. The other solution, if you have to go up high using a small mag like a slick, for example, is to pressurize the magneto. By pumping compressed air into the magneto, air is a very good insulator, and it will minimize the likelihood of internal arc over, even when the mag is relatively small and the various distributor contacts are fairly close to one another. The problem with pressurizing the mag is that it increases mag maintenance, because when you're pumping air, the compressed air from the turbocharger through the mag, you're also pumping a certain amount of moisture and contaminants through the mag, and so pressurized mags tend to have a lot more problems with corrosion and contamination, and they need more frequent maintenance than a non-pressurized mag. Also, almost all of the pressurized mag installations that I've seen use a single pressurization source and a single air filter to pressurize both mags. And if something goes wrong, for example, if the little plastic nipple on the pressurization filter breaks off, both mags will simultaneously go unpressurized, and both mags can start misfiring at the same time. So it's actually a single point failure that can take out both mags at once, which is not really the greatest idea. But at any rate, those are the two approaches that are used to address high altitude misfire in airplanes that fly up high, either using a physically large magneto like a Bendix S1200, or pressurizing using a smaller magneto but pressurizing it. Very, very important that these magnetos come off the engine and be opened up for a 500-hour inspection. Magnetos are one of these things where, because they've got a lot of very failure-prone plastic parts inside and so on, and things that wear out like carbon brushes and so on, they have to be opened up on a regular basis. And although it's not required by regulation, we're very, very religious about having the mags opened up every 500 hours. You don't have to overhaul them every 500 hours. We normally don't ask for an overhaul. We ask for what's called an IRAN, inspect and repair as necessary. Typically, the cost of doing that will be something like $400 to $600 per magneto, depending on how many parts turn out to need replaced. Normally the points are always replaced, the carbon brush is always replaced, a bunch of lubrication and stuff is done, but it's a very careful inspection, and sometimes additional parts need to be replaced. So doing these 500-hour IRANs is going to cost about $1 per hour per mag, but it's really important to do that. A lot of shops will do these in-house. We prefer not to let them do that. We prefer to send them out to a Magneto specialist, because most shops simply don't have the tools or the knowledge to do this job right. So we typically always send them out to one of a number of mag specialists around the country that do nothing but work on magnetos. The IRAN includes a complete teardown inspection, replacement of various consumables, points, carbon brushes, and so on. There's a lot of cleaning and lubrication that's done. The E-gap and breaker point gap are adjusted, and then the mag is reassembled. And if this is done at a Magneto shop, they typically have a test fixture where they can run the mag on a test fixture and actually stress test it, make sure it's putting out the right voltage, and so on. If you have your local mechanic do it, he typically doesn't have the equipment to do that. That's another reason why we like to send him out. There are basically 4 different series of magnetos that are in common use. The one on the top right is the Bendix S1200. It's a physically very large mag, very robust, produces a significantly hotter spark than any of the others, is very good for high altitude work. If you have a choice of magnetos and you can fit an S1200 on your engine, it is far and away, hands down, the best magneto you can buy. It will not fit on every engine because it is quite large. The smaller Bendix is the S20 or S1200, depending on whether it's an impulse coupling mag or a retard breaker mag, but they're basically the same mag. It's an older design, a smaller design than the S1200. It's a pretty good mag. If you run these things up at altitude, you have to pressurize them. The third one is the Bendix Dual Mag, which was not really a wonderful concept in the first place, and now aircraft owners that have engines that are equipped with a dual mag are in a world of hurt, because Continental has stopped supporting them and stopped making spare parts for them. Spare parts, a number of spare parts are still available from third-party suppliers, but there are some parts that are just simply not available. The dual mag is made by Bendix, which is owned by Continental, and is used only on Lycoming engines. What's wrong with this picture? This is probably a big reason why Continental made the decision to stop supporting that mag, because it's not used on any Continental engines. It's only used by the competition. At any rate, if you have a Lycoming engine whose model number ends with a D, that means you have a dual mag on it, and these mags are going to become increasingly problematic because a lot of the parts simply can't be had anymore. The fourth mag is the Slick mag. Slick used to be owned by Unison. It's now owned by Champion. The Slick is a small mag. It's generally less robust, less durable, puts out not as hot a spark as the Bendix mags, but they're used a lot because they're very inexpensive, and you can get an overhaul exchange Slick mag for about $800. So frequently people don't even bother to do the IRANs. They just throw them away, or don't throw them away, but trade them in at every 500 hours for an overhauled or a factory exchange mag. Not my favorite mags, but they're very commonly used. They're lightweight, they're inexpensive, and particularly slicks more than any, simply because they're less robust, really have to either be replaced or be taken all apart every 500 hours. You don't want to push your luck with a slick mag. Finally, just a couple of quick points about troubleshooting. There's a lot more about this in my engine monitor webinar, but just very quickly, if you are flying along and you see one EGT on your engine monitor rise way up above the others, that normally indicates that one plug in that cylinder is not firing. It could possibly indicate that the ignition lead is bad, but most likely it's a plug failure. On the other hand, if you see all EGTs elevated, that normally means that the entire Magneto is not firing. So the difference between a bad mag and a bad plug is that a bad plug causes one EGT to rise, but a bad mag causes all EGTs to rise. Also, if you get your airplane out of maintenance or an annual inspection or something, and you note that the CHTs are higher than you're used to seeing and the EGTs are lower than you're used to seeing, it means that the mechanic screwed up the ignition timing and advanced the timing. That's a very dangerous situation because it reduces detonation margin on the engine. So if you get the airplane out of maintenance and see elevated CHTs and depressed EGTs, put it right back in the shop. Tell them to check the ignition timing, because they probably messed it up. The converse of that is that if the EGTs are all high and the CHTs are all low, the ignition timing is retarded. That's a much less dangerous situation. All it does is cause the engine to put out a little less power, but it won't cause anything to blow up. But in any case, first time you get the airplane out of the shop after an annual or any other time that the mechanic has touched the magnetos, you want to, on your first flight, check the CHTs and EGTs and make sure that they're all where you expect them to be. And if CHTs are high and EGTs are low, or vice versa, you've got an ignition timing problem. You want to put the airplane back in the shop and have them correct the timing.
Hey, Mike.
Yes, sir.
We've had a number of questions. Oh, we're at the question.
Yes, we are. We are. Isn't that amazing? How that
amazing.
Let me just make one comment before you get into the questions, and that is, Charlie will probably not get to every question that's been answered. I have my email address up here, and if you have asked a question and it doesn't get answered, please go ahead and email me with your question, and I will try to give each of you a personalized answer. Go ahead.
Mike, you must also be clairvoyant, because there is absolutely no way we will get through all of this. But I think there's one that probably has been asked at least 6 or 7 times, and that is...
Oh, my goodness. We have over 600 people in the room. Wow.
Yeah, we had a great turnout tonight.
That is cool.
And I think Sean's probably summarizes it as well as any of the other questions. When doing a mag check with an engine monitor, why does the EGT climb when shutting off one of the mags? I would have thought the mixture would not burn as well, causing a drop in the EGT.
Well, that's a very good question, and I'm happy to answer it. Here's the way it works. When you switch from 2-mag operation to 1-mag operation, the combustion event in the cylinder has a single ignition point rather than 2 ignition points. So instead of the fuel air mixture igniting from 2 different places and burning towards the middle of the combustion chamber, which is what normally happens, it ignites from one spark plug only and has to burn all the way across the combustion chamber from that single ignition point. As a result, the combustion event takes a longer time to complete. It's a single flame front rather than 2 flame fronts approaching one another. And because the combustion event takes longer to happen, it hasn't had time to cool off as much at the time the exhaust valve opens. And when you think about it, the EGT probe doesn't see anything that's going on inside of the combustion chamber. It only starts to see something when the exhaust valve opens. So although it is true that igniting the mixture from a single spark plug puts out less energy and causes a slight loss of power, that's why we actually have an RPM drop, the combustion gas is hotter at the time the exhaust valve opens because the combustion event proceeds more slowly, but the exhaust valve opens at the normal time. It doesn't know we're operating on 1 mag. And therefore, the gas that comes out the exhaust valve and flows past the EGT probe is hotter. I hope that is an explanation everybody can understand.
I think that covers it. Okay, here's another one. Why are mags still used on general aviation engines?
3 words: FAA. Basically, the reason mags are still used on general aviation engines is because to certify an electronic ignition system, the FAA certification obstacles are extremely high. Non-Magneto ignition systems normally depend on having an external source of power, and for the FAA to accept an electronic ignition system requires an electronic source, a source of electric energy that is essentially totally bulletproof. In fact, there are requirements for it to withstand electromagnetic pulse. In other words, what would happen if an atomic bomb went off? It's always seemed to me that if a nuclear warhead went off, off my right wingtip, the loss of ignition would be my least concern. But the FAA doesn't seem to look at it that way. But in any case, the reason is that the FAA has, in their certification requirements, has created certification obstacles that make it extremely difficult for an electronic ignition to be used on a certificated engine. There are a couple of systems that are approved. They're just gradually starting to get into the stream of commerce, but the FAA has made it very, very difficult, and most of the electronic ignition systems that are in use on experimental aircraft simply won't pass muster with the FAA certification requirements, which most people think are excessive, but the FAA is the FAA.
Okay. Randy would like to know, is it still possible to do an in-flight mag check with a single EGT gauge that has been properly leaned?
Well, you can do it. You just don't get very much information. I would not hesitate to do it in an engine that just has a single EGT gauge or even no EGT gauge, just looking for whether the engine runs smoothly on 1 mag. But if there's a problem, without an engine monitor, you can't really see where the problem is. With an engine monitor, you can say, oh yeah, the bottom spark plug in cylinder number 3 is giving me a problem here. Without an engine monitor, you can't get that information. I won't go into my long spiel about why every airplane needs to have a digital engine monitor, but you do.
I think I can sum it up by the fact that I think Mike Bush would say that is the best money spent on an aircraft, right?
Pretty much.
Okay. Lawrence would like to know, does having 2 mags with impulse coupling help start in cold weather versus 1 impulse?
Well, probably so. Actually, the shower spark system is the very best. The shower spark system, because of its nature, actually fires a series of sparks rather than just a single one, and is exceptionally good for cold starting. But yeah, having impulse couplings on both mags will give you twice the chance of getting the thing to fire, and so it would be an advantage. Some impulse coupling engines have impulse couplings on both mags, and others have it only on the left mag.
Okay, John would like to know that he says, I've heard that rotating the prop backwards is bad for the impulse coupling. Others say that it is safer because the impulse coupling will not work. What's the best?
Rotating the engine backwards doesn't hurt the impulse coupling at all. Whoever told you was probably confused. The only thing that people caution about rotating the prop backwards is with carbon vane vacuum pumps, and even that I think is way overblown. But no, rotating the prop backwards will not hurt an impulse coupling one bit.
Okay. And Mike would like to know, what's the difference between the IRAN work and an overhaul?
Basically, the difference is that when you do an IRAN, you give the Magneto tech discretion to replace only the parts that look to him like they need to be replaced. When you specify an overhaul, you take all the discretion away, and the tech has to replace every single part that the overhaul manual requires, which is essentially everything that could possibly wear. So, for example, an overhaul, he has to replace the bearings. An IRAN, he looks at the bearings. If the bearings look good, he keeps them. If they don't, he replaces them, and so on for lots and lots of other parts. Also, the overhaul requires that the magneto rotor be remagnetized. An IRAN normally doesn't. So there's just a bunch of stuff like that. But we prefer to send the mags to mag experts and then give them the discretion to decide what needs to be replaced and what doesn't.
Okay. And if you need to find a mag expert, how does one go about finding that person?
Tell you what, anyone who would like a list of our preferred Magneto shops, drop me an email and I will send you back. God, how many emails am I going to get with 600 people in the room? That's a little scary. But at any rate, I'll be glad to, if you email me, I'll be glad to send you a list of Magneto shops that we like to use.
Okay, and then David would like to know, is there a max number of hours on a mag before they should be totally rebuilt or replaced? And does it make a difference by the make of the mag?
And the answer is no. If you do an IRAN every 500 hours, the parts that are worn or getting too old, for example, condensers tend to get replaced on age. They all have a date code on them. Will wind up getting replaced, and some IRANs will be a little more expensive than others because the MagTech decides to replace more parts. But no, you can run mags indefinitely as long as you have an IRAN done every 500 hours by a mag guy who knows what he's doing.
Okay, and
unless you have a dual mag, in which case eventually you're going to be out of luck.
Okay, Jose would like to know, when checking mag external timing, is it absolutely necessary to use a prop hub degree indicator? Can one just rely on flywheel marks relative to the engine split line? My Lycoming has the flywheel timing marks.
You know, I don't know the answer to that for a Lycoming. I know on Continentals, Continental came out with a service bulletin that said don't use the timing marks because they're not accurate. I honestly don't know the answer on the Lycoming whether Lycoming allows you to use those or not. Sorry.
Okay, and Nick says, you've described the in-flight mag check in another recent webinar. I tried it on my twin Cessna a couple of weeks ago, and both engines ran too rough on one mag for me to leave it running that way for 30 seconds. I was in Lena Peak cruise. Does that mean I should have tried the test more rich, or does it mean I observed a problem with both engine ignitions?
Probably means both of those. But if you're saying that it ran uncomfortably rough on one mag but not the other, then for sure you've got an ignition problem that you need to look at. If you were running uncomfortably rough on both mags, then possibly you were just running it a little bit too lean. But it sounds from the description that like the mag test did exactly what it was supposed to do, which is to tell you got a problem.
Okay, and Lawrence feels that the in-flight mag checks are not a good procedure. If one mag isn't running correctly and the engine is running at full power, then you get a substantial backfire when the operating mag is turned back on. This is a bad idea in the hands of most pilots. Bye-bye exhaust baffles, if equipped. Thoughts?
Yeah, two thoughts. One is I would concede that it's probably not a good idea to do this with your wife in the airplane. And the other thing is that if on the very odd chance that you have a completely dead mag, which is an infinitesimal chance because you've done a pre-flight mag check, and if you had a dead mag, you'd know it before you took off. But in the infinitesimal case that you do actually have a bad mag that developed in the air and the engine quits, you do not turn the key back on. You pull the mixture control, you turn the key on, and then you very slowly advance the mixture control. If the engine quits because the ignition went away and the prop is still windmilling, fuel and air are pumping through the engine, they're just not getting ignited, and the exhaust system gets full of unburned fuel and air, and then when you turn the key back on, of course it ignites all that stuff and creates it's not a backfire, it's actually called an afterfire, but it very, very rarely will damage exhaust components, but it'll typically scare the hell out of you. So if the engine quits, and this is not just a matter of a mag check, but if the engine quits, you do not want to turn it back on with a key. You want to pull a mixture, which now causes air with no fuel to be streaming through it and to clean everything out. Then turn the ignition on and gradually bring the mixture back up, and that will eliminate the problem.
All right, and Harley would like to know how long does it take you to do your pre-flight mag check the way you described?
The pre-flight mag check?
Yes, when you're using the EGTs versus the
30 seconds, maybe?
Okay.
I don't know, 30 seconds, 45 seconds? It doesn't take any different amount of time than it would looking for the RPM drop. You're just looking at a different instrument.
Okay, and Jim would like to know if you have any advice for hot starts.
For hot starts, well, I probably shouldn't get into that here because it's a very long discussion, and it's different for different engines. It's different for carbureted engines. It's different for injected Lycomings than it is for injected Continentals. So that's probably not a question we ought to try to do here.
Okay. Paul would like to know what should appear in a logbook entry regarding mags for an annual.
What should appear in a logbook entry? It depends on what was done. If nothing was done, then nothing would appear in the logbook entry. I'm not sure I understand the question.
Well, he says is Appendix D enough, so I assume he's
yes, Appendix D is always enough.
Referring to the scope, and he's probably an amateur builder, and he's probably referring to the scope and detail of Appendix D, would be my guess. Yeah,
and again, you normally wouldn't write anything down. If you did an annual inspection, you'd say, I certify that this aircraft has been inspected in accordance with an annual inspection in accordance with Part 43, Appendix D. You don't say any more. You don't say, I did something with the mags, unless you actually did maintenance to the mags.
Okay, here's a question, Mike. Is there a chat room associated with this webinar? If so, what is the link? We don't have a chat room. However, Mike, I believe you started in the EA forums a maintenance section, correct?
Yes, we have a maintenance workshop forum on the new EAAforums.org. Is that right? EAAforums.org site.
EAAforums.org. Yep. Mm-hmm.
And it has gotten to be a very active and vigorous forum, and it's a real good place to bring maintenance related questions. And
you are pretty much monitoring that one, correct?
Yes, I am officially the moderator for whatever that does. Sometimes I have answers. Sometimes there are people there that are a lot smarter than me that have answers.
Because you didn't have enough to do. add
Right.
all the questions from tonight, and you know,
Right.
you might be busy.
And that one was all my fault because I said, how come you guys don't have a maintenance forum in these EAA forums? And lo and behold, 3 days later we had one.
That's right. Okay, David would like to know, is there a replacement for the dual mag on a Lycoming TIO 540 S1AD?
Well, there is, but the problem is that you really can only change mags at engine overhaul. All of the Lycoming engines, I believe, have non-D versions, but they require a different accessory case, an accessory case that's set up to mount 2 individual mags rather than the one dual mag. So it's not something you can change except when you overhaul the engine, and when you overhaul the engine, you can get a different accessory case installed, and the engine turns into a non-D engine. Unfortunately, nobody makes like a little handy-dandy adapter or anything like that would allow you to mount 2 conventional mags on a Lycoming D suffix engine that's set up for the dual mag. It's kind of a bad deal. I feel sorry for people with D engines because Continental just made this decision to leave them high and dry.
Okay, and Gerard has the question of, would you switch from non-impulse mag-equipped engine to impulse mags when the engine does not have a starter system and hand propping is mandatory?
Well, if hand propping is the way you start the engine, then you have no choice but to use impulse couplings. A shower of sparks won't work. So yeah, you need to have impulse couplings if you're going to hand prop the engine.
Well, Mike, just to clarify, I don't believe I had impulse couplings on my Champ 65 horse when I was hand propping it.
How did it start?
You just had to swing it fast.
No, but well, I sincerely doubt that.
Okay, because I can guarantee you could never, there is not an audible click ever. So I think that's what this fellow has too.
What engine is this that you have?
It was a 65 A65 Continental.
Wow. Well, I have to admit, Charlie, that I have never worked on an A65, so I guess I need to do a little homework. But
I know it's a little low on your horsepower range.
Well, it's just hard to imagine that a non-impulse coupling mag could generate enough voltage to start the engine at hand propping speeds. But I could be wrong. I'll check it. I'll check it out for you.
All right. Well, John's chimed in and says Charlie is right about no mag on an A65.
No mag? Or no
I think he means no
coupling?
impulse, but I'm sure somebody else will chime in as well. I might have missed this part, but Gary would like you to explain more about the tool from Home Depot.
Oh no, I was just talking about a digital inclinometer, a digital level to use instead of the dunce cap arrangement with a little swinging pointer. You can buy digital levels or digital inclinometers that have a little digital readout and a little button that you hit to zero it, and you rubber band it to the propeller instead of using a dunce cap, and it's just much more accurate. Okay,
and Thomas just chimed in with lots of A65s do not have impulse couplings. They do backfire more frequently.
Okay, well then I stand corrected because that's a place that I have never gone.
And Doug just chimed in with there's a free iPhone app that has an inclinometer.
Oh, heck, cool is that? I'll have to check that out.
Oh, what will they think of next?
Absolutely.
Okay, Ralph says, I have just reached 500 hours on my mags. My mechanic said he will inspect the mags for wear. How long do mags normally last? My plane is a 1981 Piper Dakota.
Mags normally last forever if you take them apart every 500 hours and replace anything that's getting worn out. I mean, the only thing that would prevent a mag from being reused is Well, if the case cracks, then it has to be rejected. There have been cases where something was damaged inside a mag, and a pole piece started rubbing on the rotating magnet assembly, and so the rotating magnet assembly was not reusable, and at that point it's not really economical to repair it anymore. You have to replace it. But generally speaking, unless something really ugly happens, you can keep a mag in service basically forever as long as you do a 500-hour IRAN.
Okay, and Brian has 2 slick mags that he hasn't used yet. Are the carbon brushes something I should consider replacing with new? How would I know if the brushes are like the ones that you referred to in the presentation?
There's an AD, and the AD has a specific applicability section that gives dates during which, if the mag was either manufactured or rebuilt during a particular particular date range, then it's one that might have the bad brushes, and gives inspection procedures for opening up the mag, looking at the brushes, and seeing if you've got a bad one. So you just need to pull the AD. I don't have the number at my fingertips, but it's easy enough to get with Google, and take a look at the AD and follow it.
Okay, and Ronald would like to know, you showed that picture where the gear teeth had broken. Would that be from wear and tear, or what would be the failure point on that?
Well, there are a number of ways that those teeth can fail, and unfortunately one of the most common is mechanic error. There's a tool that mechanics frequently use to hold the gear stationary when adjusting the E-gap, and if they don't remove that tool before trying to install a mag on the engine, the gear teeth can become overstressed and can break off. There are also other reasons that it can happen, and also if the gears get too old and the plastic just starts getting too brittle, it can start shedding teeth. So there are a number of reasons that can happen.
Okay, and Joseph asked, if you haven't yet, can you explain about the E-gap in some detail? Let's see. He's gathering information in an experimental environment.
Yeah, you probably don't want me to do it in some detail because we probably don't have enough time. But basically, the E-gap adjustment on any of these mags consists of, first of all, rotating the rotor until it gets to what's called magnetic neutral. And as you rotate the rotor inside a mag by hand with the magneto off the engine, of course, there's almost a magnetic detent you can feel where the poles of the rotating magnet are aligned with the pole pieces of the coil, and then you measure the number of degrees you have to turn the rotor from that magnetic neutral to the point where the points open, and there's a specific number of degrees that's supposed to be, and if it's not correct, it's adjusted in 2 different ways depending on whether it's a Bendix mag or a slick mag. If it's a Bendix mag, which has a real honest-to-God metal cam on it, the cam has a screw that you can loosen and actually rotate the cam slightly with respect to the rotor and get the E-gap exactly correct. Slick mags don't have a real cam. They've got that little chunk of plastic that installs in that groove on the rotor shaft. So the only way you can adjust E-gap on a slick mag is by adjusting the points. And slick gives you a very wide range of acceptable point gaps so that you can adjust the point gap to be larger or smaller in order to get the E-gap, or this number of degrees between magnetic neutral and the time the points open, to be correct. That's probably all I should say on the subject. you want to know more, both manufacturers have Magneto maintenance manuals that go into great detail on all that stuff.
Okay, and Chris chimes in with, according to Paul Milner at CFO, quote, there's only 3 parts not available in the aftermarket for the DMAGs, according to Kelly Aerospace, and those approvals were in process. So maybe there's some hope on the horizon for the DMAG people.
That's good. I know we had a client recently who needed a replacement impulse coupling spring, and they just were unobtainable. But I guess it's good news that Kelly is going to be getting approval on those parts. It's bad news that it's coming from Kelly. Actually, it's probably not Kelly anymore. It's probably Hartzell Engine Technologies, because they bought Kelly, or most of the Kelly stuff. But their quality assurance has not been the greatest. But at any rate, it certainly is good news if those parts are going to become available.
Okay, Mike, great webinar. We've pretty much hit our allotted time. Just to remind everybody, Mike does a webinar the first Wednesday of every month. The only exceptions being maybe if there's a holiday or AirVenture right in there, then we might move it back a week. But the next one, if you'd like to mark your calendar, is deciding when to overhaul, and that is on February 1st. Am I correct on that, Mike?
That's right. And this is a brand new webinar, and it's going to be a real interesting one. The subject is when to overhaul, and the answer is not at TBO. Let's leave it at that.
You're tipping your hand. Any closing thoughts tonight, Mike?
No, I'm kind of blown away by the turnout. I hope the trend continues. And if the trend continues, you're going to have to figure out what we do when we get to 1,000.
Well, somebody said I got to buy the beer if we get to 1,001.
All right.
I said I hope I have that problem. One reminder.
Actually, this time of year, it's probably going to be hot chocolate, right?
Yeah. One reminder is if you do want to see either the recording of tonight's webinar or any of Mike's previous webinars, simply go to eaa.org/webinars. And we have a red button. You can't miss it. It says Webinar Archives, and you can get back and review any of the previous ones Mike has done. So if you want to go back and see his engine monitoring one or any of the other ones he's done, go check them out. Thanks, everybody, for tuning in, and thanks for being an EA member. And stay warm tonight. Good night, everybody.
Thanks, everybody.